Good day, ladies and gentlemen. Welcome to Linear Relationships lesson number 3. And today we're going to be looking to write a linear pattern based on being given 2 data points within the pattern. Our goal is going to be to compute the rate of change, the slope, change in y over change in x, as well as the initial or beginning amount, the y-intercept. Our objective will be specifically to write linear relationships or repeated addition patterns being given 2 data points based on what I just described above. Let's please remember that linear relationships are simply repeated addition patterns, and they are a result of a constant amount being added over and over again. If we're adding a negative text, we could argue that we're subtracting, and the relationship would be going down. Linear relationships therefore either increase or decrease by the same amount over and over again. We're either adding or subtracting or adding the opposite over and over again. They're very predictable. A linear relationship, because it's so predictable, it's identified as a first-degree polynomial. That would suggest that the exponent is a 1. When we start to change the exponent to all different numbers, the behavior can change significantly. The most common form or formula of a linear relationship is in slope-intercept form, and it's known as y equals mx plus b. In that form of formula, what we're able to identify is that m is the rate of change. It's the constant amount that we're adding over and over again. Can I argue that it's like multiplication to me? It does, but multiplication is just repeated addition. B, ladies and gentlemen, is the constant numerical value. It is the beginning amount. It's where our number pattern will start, and then we'll add the same m over and over again as we increase it. A more common presentation, or a more useful presentation, I should say, happens in the calculators where they're called ax plus b or a minus bx. They're all going to give us some information, and we'll talk about why each one is different and useful in different ways as we move forward. Because you have m and x right next to each other. And when you have amounts next to each other, mathematics no operation, so automatically multiplication. But as we had just suggested, and as we repeat throughout the year, multiplication is just repeated addition. We're just adding the same amount over and over again. Because of the constant amount being added over and over again, the graph is going to appear as a straight line. That's going to change as we get to some of the more complicated relationships moving forward. But for now, this is some really easy stuff. The constant amount of change is known graphically as the slope. We identify it as the variable m, and can be computed or observed as the computed difference in y's over difference in x's, where y is what we're measuring or observing, and x 90% of the time will be time. It's sometimes called the average rate of change, the slope, because we're looking at the change in measurement amounts y over the change in x. So it's describing the exact same process as in the first presentation of this formula. The only difference is we're using triangle, which means delta in Greek or change. So you could have the difference in y's in the first presentation over the difference in x's. We take the difference in subtraction. Or you could call it the change in y's over the change in x, just for simpler purposes. Or graphically, we like to identify it as the rise over the run. And since on a graph, the y-axis goes up and down, that would be change in y, similar to what we saw in the previous 2 presentations. And since the x-axis always goes left to right, the horizontal axis, that would be the run, the change in the x-axis. Again, all consistent. All 3 formulas tell the same story. They just look at it a little bit differently. Let's get to work. In the first portion of the classwork for today, you're going to have some independent work to do. I'll get you started on each of them, then I'll give it a pause and let you go to work. In Roman numeral 1, I'm asking you to identify the slope of the rate of change m, as well as the y-intercept, the initial amount, or the beginning amount in each linear relationship. Sometimes it's helpful to think of m as what we're multiplying x by. That's why it's being called m. Just don't get confused, and remember that throughout the unit, multiplication is going to be repeated addition. So if you need to identify m and b in the first relationship where our y's are decreasing by 3 over and over again, starting at 3, so you can imagine that 3 would become 0, then it becomes negative 3, then it would become negative 6, and so forth. That's what the pattern can suggest as we continue to add negative 3 or subtract 3 over and over again. You could write y equals mx plus b across the top, and you could identify the rate of change m as negative 3 over 1. We like to write as a fraction rise over 1, simply decreasing 3 every 1 unit of time. And b, the beginning amount, we prefer to write as 0, comma 3, indicating that at time 0, or if we do 0 subtractions of 3, that the value of the relationship will actually be 3. So that's starting, we'll be doing that. In a moment, I'm going to ask you to do 2 through 4 on your own. For Roman numeral 2, ladies and gentlemen, we're going to determine the equation of a linear pattern from the given information. So I'm suggesting to you in number 5 that if you have a relationship, linear relationship whose slope is negative 4, or rate of change, or repeated addition, and the pattern starting at negative 2, could you possibly write a relationship to describe that? Now, in this instance, you should know that technically what we're talking about is starting at -2 and subtracting 4 over and over again. -2 is going to become -6, then -10, then -14, and so forth. We would describe that by saying y equals -4x. Slope is the rate change n. If you have to write y equals mx plus 3 to remind you that n is going to have to be multiplied by x. And then we have to do -2. That is the beginning amount of the value at time 0. You could have used the commutative property and said 2, couldn't I suggest that this is starting at -2 and we're subtracting 4 over and over again x number of times? Yeah, how can we do that, Teach? Commutative property means we change the order of addition or multiplication, not subtraction. But we have to remember that technically we have -4x plus -2, because subtraction is going to go in the opposite. And then in that instance, we could do -2 plus -4x, so that we would look at that way, so we could just do -2 minus 4x. Take a moment to see if you can complete numbers 2 through 4 and 6 through 8. Pause the video and see together. Assuming you pause the video appropriately, you can now come back and take a look. Number 2, y equals mx plus b, y is equal to twice the value of x. There is no amount being added, therefore the relationship is starting at 0, and we're just adding 2 over and over again. If x is 0, and we add 2 no times, then y would be 0 as well. So when x is 1, y is twice that, it is 2. Then when x is 2, y is 4, so this pattern goes 2, okay, 0, sorry, 2, 4, 6, 8, 10, and so forth. The rate of change is 2 over 1, rise over 1, the intercept is 0 times 0. For number 3, there are no x values being shown at all, therefore no x values must mean the rate of change is 0, and we're starting at a beginning amount of 4, and we're staying at 4. This is going to become known as a constant function because the relationship is always 4. I'll make a prediction, it's always going to be 4, it's never going to go up, never go down. And our constant functions are going to appear as horizontal lines. When we graph them, wherever 4 is, we'll start there and we'll stay there. It'll never go up or down at all. It'll have a slope of 0. Number 4, ladies and gentlemen, the amount of money borrowed and owed to a college each term. So it looks as though they're starting by borrowing $12,000 to get to college, or maybe that's the tuition, and then they're going to spend an additional $4,000 each term. Maybe that's room and board. The rate of change is a decrease of $4,000 in the person's money because they're going to owe that to get through that term, and they're borrowing the tuition. They're starting at -12,000, going up by $4,000 each term, and it's a lot more than that. I wrote this question many years ago. Number 5, n is 2/5. We're increasing 2/5 each time, starting at 3. Y equals 2/6x plus 3. Number 7, n is -1. Y equals -1x plus 0, which is more efficiently written as -x. And number 8, if the temperature of water in a pool heated by solar panel per hour could be described as a rate of increase of 3 degrees per hour, and the pool starts at 55 degrees, you could write that as y equals 3x plus 55. If you want to include more appropriate variables for this circumstance or in the context of the question, you might use T, because we're measuring temperature, equals 3 degrees per 8 per hour plus 55. You could also say T equals start at 55 and increase by 3 degrees per 8 hour. And that might be a little more interpretive as well. So let's take a look at Roman numeral 3, and I'm going to have to do that one with you. I often assign this to students as part of the do now, but I know that they're struggling to get in a good routine, so we can do it together. Number 9 is suggesting that we have a repeated addition pattern with slope or rate of change of -2 or decrease of 2 over and over again, and it goes through the point 2, 4, meaning that 2 units time from now, it's going to measure 4. We're going to be able to use that information to help us determine the linear relationship. We know what m is, it was given to us, we just have to determine b. And eventually we're going to take a look at this in the table of values for tomorrow, and we're going to say, isn't it possible to just say that 2 units times from now the relationship measures 4? And don't we simply want to know what the relationship measured at the beginning? In the beginning would be times 0, x comma y. And we're going to be able to say, well, why don't we, if we're subtracting 2 over and over again, if the relationship is supposed to go down, why don't we reverse the pattern and go backwards and add 2? And couldn't we say that it should have been 6 one moment of time ago, and if we add 2 again, it should have been 8 at the beginning value? That's possible, but we're going to look at it a little more formally using the formula. So using the formula, we would rewrite our most common formula, y equals mx plus b, and we would choose to substitute in place of y, m, and x to solve for the value of b. We've been given measured amounts for all those variables, and we can substitute them in appropriately. According to the point that we're working with, it suggests that y is 4. So we're going to begin by substituting 4 in place of y, And we'll say that that is equal to m, which is negative 2, and x, which is positive 2, according to the point in time that we're working from. And we're going to add that to b, and that's to be equal to 4. If we simplify the expression, negative 2 times 2 is negative 4, and we need to add that to b to equal 4. And the question becomes, what do we add to negative 4 so that the value is positive 4? Undo that subtraction with addition, or add the opposite, add 4 to both expressions, and we find that the beginning amount of this relationship must be 8. This relationship is a one that starts at 8 and is going down by 2 over and over again. Y equals negative 2x plus 8. Or as I've grown to prefer, y equals start at 8 and subtract 2 over and over again x number of times. For number 10, write a linear equation for the amount of a certain hormone if it is increasing throughout the body at a constant rate of 125 parts per day, and after 14 days is measured at 3,000 parts. 14 times 3,000, x comma y. Coordinate pairs are measured out on the graph. The x variable, the unit of time, comes first always, and the y variable we're measuring is the second component of that ordered pair. So if we want to write a linear relationship, if you know a formula test, you should always write it, right? Y equals mx plus 3. My hope is that you understand that in order to solve, to write a linear relationship, you need to know what m and b are. M, ladies and gentlemen, is the rate of change, and we're told that in the question that's 125 parts per day. And B is the beginning amount, and we don't know what that beginning amount was, what the hormone pattern started at day 0. We know what it measures at day 14, but not at day 0, which we must have to write an appropriate linear relationship. We need the rate of change and the initial or beginning amount. So we're going to rewrite our formula, y equals mx plus 3. We're going to substitute in for y and x appropriately. So y is kind of our total, if we know total related. 3,000 parts is the result of going up 125 per day for a total of 14 days. And we've got to add b block. 3,000 is going to be the result of 125 times 14, which is equivalent to an increase of 1,750 units of that hormone, plus the beginning amount. We now have to subtract 1,750 from both expressions. And I believe that we get 1,250 as the difference equal to the beginning amount. Therefore, we could write this relationship as an increase of 125 units of the hormone x number of times, starting at 1,250. If you want to substitute in some variables in the context of the question based on the story you just written, you might say H for hormone, that's what we're measuring, is equal to 125 parts per D per day, or maybe 2 per time, starting at 1,250. Or if you want to use the community property of addition, you could reverse those things. That brings us to today's content, and the main objective of today is to be able to write those same linear patterns we just saw above without being given the rate of change, the slope. So we're going to use our knowledge of linear equations to help write equations for each line from the two given points. And I need you to remember that you're going to have the slope of the rate of change m as well as the y-intercept of the beginning amount b. And to write an equation of a line m, we have to recall the slope is either the change in y over the change in x, the difference in y's over the difference in x's, the rise or the rise over the run. We use the beginning of the initial amount as the value of the relationship at size 0, and it can be found by substituting in for y, m, and x in slope intercept formula. So if we want to write the equation of a line that goes to the points 1, 4, and 3, 8, the first thing we need to do is recognize that we do not have the rate of change. We don't know what the slope is, or how this is going up over and over again by the same amount. So we're going to have to compute it. The slope formula is typically difference in y's over difference in x's. So we label our points x1 and y1, and x2 and y2, indicating the first observed time, 1 moment of time from now the pattern measures 4, and the next time we observed it, when in time 3, the pattern measured 8. So in order to approach, some students will make a quick little table out of this, and if they teach, can't you just say that at 1 unit of time from that measures 4, at 2 units of time from that measures 8, can't we take the difference in y, it's an increase of 4, can't we take the difference in x, it's an increase of 2, and can't we say that if we're going up 4 every 2 units of time, shouldn't our rate of change be 2? Let's do the formula. Then we do the formula and we substitute into the slope formula. I like to identify y2, which belongs in the first position of our numerator, by circling it. I identify y1, belongs in the second position of our numerator, And then I do the same thing, or I double underline my x's as I substitute them inappropriately into the formula. Time 3 was when I finished measuring it. We began measuring it at time 1. And the difference in the measured amount is 4 in the numerator. The difference in time is measured as 2. So it went up 4 measured amounts of 2 units of time. And another way to say that is 2 over 1 or just 2. That is our m. M equals 2. Now that we know m, we'd have to go back and find b. And in order to find b, we have to use either of the 2 points. It doesn't matter which one. They're going to bring us to the same beginning amount. I often select the first point to work from, and I'll substitute into y, m, and x. From the first point in time is measured, y is 4, and we just determined is 2, and x we know for that first point was 1 plus 2. So we're able to say that 4 was the result of adding 2 to the beginning amount. What do you add to 2 to get 4? Well, if you continue to solve and do addition and subtraction, you're going to find out that 2 has to be the value of 2. This is a linear relationship whose slope is 2 and rate changes to y equals 2x plus 2, or y equals start at 2 and add 2 over and over again x number of times. And if I took that little table I had selected, or had written 1 comma 4, 3 comma 8, if it's supposed to go up 2 over and over again, at time 4 this should measure 10, at time 5 it should measure 12. If we wanted to undo the addition and subtraction to work backwards in time, we could say that if you subtract 2 from 8 at time 2, it should equal 6. If you subtract 2 from 6 at time 1, it should equal 4. Yay, it does. And if you subtract 2 from 4 at time 0, it should equal 2. And we're able to confirm that. We'll see more of that with tomorrow. Flip. On the back, ladies and gentlemen, we could do the same thing for the next question. We're asked to write a linear relationship from 2 points. We should label those 2 points x1, y1, indicating the first time we observed the relationship in the first measured amount, as well as x2, y2. We would have to determine the slope as well as the initial amount to write a linear pattern. So we begin with the slope formula. We substitute in appropriately. The first time we measured, the final measurement of this relationship is -2. And the first time we measured this relationship, it was -5. So we're going to take the difference between what it ended at and what it began at. And if we do similarly for the x variable, we finished predicting 1 moment of time ago, and we started predicting 2 moments of time ago. I would type this computation into the calculator because it could get a little confusing with all those negative signs. Subtraction is the same as adding the opposite, heat, change. And you could get 3 in the numerator, which is an increase of 3. Heat, change, and you get 1 in the denominator. So actually, as confusing as it is, this relationship that we're kind of observing in the past, that's what negative time would indicate, was going up 3 measured amounts every unit of time. Now that you know m, we have to find b. It doesn't matter which point you use. I typically use the first one. The measured amount at time for the first observation is -5. That's our y value. It should be substituting that in parentheses, so keep skipping that. We just determined that the rate of change is 3, and that that must have happened 2 units of time ago. And now we can find b. Simplify the expression. We must have subtracted 6 to go backward in time from the beginning amount if we did it 2 times. And if we add 6 back into both expressions, we can find out that solve for b, this relationship must have started at time 0, or would measure at time 0, 1. So now that we know m and b, we can write that this is a relationship that is having 3 added over and over again, starting at 1, or start at 1 and add 3 over and over again. If you think about it, if you start at time 0 at a measured amount of 1, and you add 3, that would become 4 at time 1. If you add 3 again, that would become 7 at time 2. If you go backwards in time, if you subtract 3 from 1 moment of time ago, this would measure -2. Hey, look at that. -1 comma 2 and -2. That works. And if you continue that pattern, 2 moments of time ago, if you subtract 3, that 2 moments of time ago, it should measure -5. Cool. It gets a little more tricky when you start to do some of the real-life examples and you have to do it on your own without us guiding you through it. So I'll take you to number 14, which is one of my favorite questions of the year. And then I'll have you work backwards and do an independent practice on number 13 to make sure you understand the concept. Writing an equation to model a predictable hormone level of a pregnant mother if her pregnancy hormone, HCG, levels were increasing at a constant rate and were measured 22 days after conception at 1,875, 22 comma 1,875, and again 32 days at conception, where they measured 2,225, 32 to 25. Okay, so the most important thing here is that you understand that you're asked to write a linear equation. When you're asked to write a linear equation, most often we immediately write y equals mx plus c to recognize that the linear pattern's most common form of formula is slope-intercept form, and we just need to determine the rate of change that's being added over and over again and where this pattern started. In order to do that, we've got to compute m, which comes from the slope formula, so we've got to write m equals y2 minus y1 over x2 minus x1. Label the points x1, y1. First measured time we observed it 22 days from that, and the first measured amount, and label the second point x2, y2. Once we've done that, substitute the slope formula using parentheses. So we're going to do y2. The final measured amount during this observation period is 2,225, and we'll subtract out the beginning measurement. And we're going to put that over the difference in time. We finished measuring 32 days of conception, and we started measuring 22 days of conception. As we simplify the numerator, I believe that is going to be 350, I hope. My calculator keeps losing my screen, so I'm not going to use it again. Over 10. And if we simplify that relationship, 350 divided by 10, that's going to come out to 35 units of the hormone, HCG, per 1 day. This is an awesome question. I'm going to come back to this in class. It really is absolutely fascinating. And we'll talk about how incredibly powerful that is. So now what we have to do is, now that we've got m, we've got to go ahead and get b, which requires us to rewrite y equals mx plus c, and to substitute in for y, m, and x. It doesn't matter which of the two data points you use. I usually use the first one because the numbers are smaller. And the total for that first one is 1,875, which must have been a result of going up 35 per day for a total of 22 days plus the beginning amount. 1,875 is going to be the result of, and I'm actually going to use my handheld calculator to prevent my screen from freezing. So that'll be pretty frustrating. 35 times 22 is going to be 770 units of increased hormone over 22 days, starting with B. Subtract 770, subtract 770, and we find out that 1,875 plus 770 is 1,105. Now that we know B, we can write a linear relationship for this linear equation to describe this pattern. We're going up 35 units of the hormone per day, X number of times, starting at 1,105. Or if you want to use variables in the context of the questions that better describe what we're talking about, you could say that the hormone level is equal to 35 per D per day, starting at 1,105. Or if you prefer, you can use the communicator to say the hormone level started at 1,105 and it increasing with 35 per day. If you got a little more time, please give number 13 a shot, and then I'll review it and see how you did. You can use either of the two questions, 12 or 14, as a model. Pause the video and see if you understand the concept. If you were successful with completing question number 14, your work should look like mine. Typically throughout the year, I'll say that your work should be as neat as mine, if not neater, as complete as mine, if not more complete. You should make sure that you show all the appropriate steps. Once you've identified m is -2 and b is -3, you can substitute those variables appropriately into your linear relationship as y equals -2x minus 3. Here's a test that's associated with it. We can take a look at that in class, but I don't want this video to get too long, so I'm going to cut it off there. Ladies and gentlemen, this is the lesson on being able to write a linear pattern given two data points in the pattern. I hope you understand that the most important portions of it are going to be that you begin by writing y equals mx plus c, and understand you must solve or compute m first, the rate of change, which being repeatedly added over and over again, and then substitute for y, m, and x, and determine b, the beginning amount. I'll see you in class. Take care.